Our next talk is Ziyu Chen from Duke University, and his talk is SpecNet2, Orthogonalization-free Spectral Embedding by Neural Networks. Now it's your time, Ziyu.
Okay. Oh, hello everyone. I'm Ziyu Chen. So I'm currently an assistant research professor in the math department at Duke University. And it is a great pleasure for me to be here to introduce our work, which is SpecNet2, Orthogonalization-free Spectral Embedding by Neural Networks. So this is joint work with Yingzhou Li. He's an assistant professor in the math department at Fudan University, and also with Yuan Chen, who is now an associate professor in the math department at Duke University. So the outline of my talk includes several modules. So first is to review or introduction to the spectral embeddings, and then summarize our contributions, and review of previous work, SpecNet1, and then we go to the unconstrained optimization and introduce our proposed different gradient evaluation schemes, and then we go to our main part of our work, which is SpecNet2 and its parameterization and training. So finally, we will show some numerical results to demonstrate the performance of our proposed spectral network, and we will conclude by the future work of our SpecNet2. So let's get started. So first, let's take a review of the spectral embedding. So what is spectral embedding? So before we give the mathematical formulation, we summarize its usage. So first, spectral embedding can be used, for example, as a dimension reduction method, or it can be used to do the spectral clustering, as in the two-moon simple example. Also, spectral embedding can be used to reveal the underlying topology of a dataset. So as shown in these four subfigures, which is from the Koifman's 2005 diffusion maps paper. So what is spectral embedding? So mathematically, given a data set which contains n samples in Rn, so we first construct an affinity matrix W. So such that Wij, so its entry Wij measures the similarity between I sample and the J sample. So typically we would assume each entry would be non-negative. So such that W is a real symmetric matrix. And one way to construct the affinity matrix is to let each entry of W, for example, Wij equals some function h evaluated at the square of the two norms of the xi minus xj, or we say square of the distance between these two data samples, and scaled with some bandwidth sigma. So h can be a non-negative function on 0 to infinity, defined in 0 to infinity. For example, it can be a compactly supported, or it can also have exponential decay. So the well-known example is the Gaussian function. So these were used earlier in the Laplacian eigenmap and also in the diffusion maps. And another way to build the affinity matrix is to use the KNN graphs, so which is a k nearest neighbors. Also, we can further tune the sigma. So in the first example, I said a sigma is bandwidth, so it can not be it can be a constant, or it may not be a constant. So if the sigma also changes with the data points, so we can further extend this affinity matrix as a self-tuned bandwidth. And given the affinity matrix W, we can further define the degree matrix D of this affinity matrix W, in which D is a diagonal matrix. So basically, D is the row sum of this affinity matrix. And we further define a matrix P, which is D inverse times W, which is row stochastic, and it can be viewed as a translation or the Markov matrix of the random walk on the graph. And I minus P, so I is the identity matrix minus this D inverse W, is called the random walk graph Laplacian of this data set. And it can be proved that it has real eigenvalues, and with eigenvectors, so denoted as in this formula. And in most cases, when the graph is connected, we know that the first eigenvalue or the smallest eigenvalue of this random walk graph Laplacian is equal to 0. And if we order all the eigenvalues of this random walk graph Laplacian, so lambda1 it refers to the trivial eigenvalue, which is 0, and also psi1, which is the trivial eigenvector, is a constant vector. And also, if we skip the first trivial eigenvalue and eigenvector, and we use the eigenvectors start from the second one. So for example, if we use psi2 until psi k, so this k minus 1 eigenvectors can provide us with the low-dimensional embeddings of the whole dataset X. So for example, we can embed each dataset point xi to capital psi xi, so where each coordinate is given by the respective eigenvectors of the graph Laplacians. So for example, the ith data point is mapped to a point in Rk minus 1. So the first coordinate of the mapping of xi would be the ith coordinate of the second eigenvector, and the last one would be the ith coordinate of the kth eigenvector of the graph Laplacian matrix. And if we generate this Laplacian eigenmap, we can see the later work, which is diffusion maps, which incorporates a diffusion time. So if you compare these two, so we scale each psi I with lambda I to the t's power, where t is greater than 0 and called diffusion time. So let me briefly introduce the embeddings of this and say why spectral embedding can reveal the underlying topological structure of the dataset. So here, figure A is a spiral, and B is the density of the spiral, and C is the Laplacian eigenmap, so computed from this dataset, spiral dataset, and without density correction. So x-axis is the first non-trivial eigenvector of the Laplacian matrix, and the y-axis is the second non-trivial eigenvector of the Laplacian matrix. And subfigure D is the diffusion maps with density correction. So we will skip the detail of what is the density correction. So basically, this would introduce you with how spectral embedding can reveal the underlying topological structure of dataset, because basically subfigure A is spiral and is topologically equal to S1, the unit disk, right? So D, if we use the two-dimensional embeddings of this spiral, even using the Laplacian matrix, it certainly reveals the S1 structure of this spiral. So one may ask why and when the mapping psi xi we just gave as a spectral embedding can be the restriction of some underlying eigenfunction in the continuous space, so evaluated on the dataset X. So suppose we are given sufficiently many data points, can we view as the eigenvectors of the graph Laplacian as some continuous functions evaluated at those discrete data points? So this theory can be summarized as the spectral convergence. So when data points are sampled on a submanifold, eigenvectors and eigenvalues of this random walk graph Laplacian would converge to the eigenfunctions and eigenvalues of the limiting differential operator L when the number of data points goes to infinity, and also the bandwidth sigma scales with the number of samples in certain way. And in particular, when data points are uniformly sampled on the manifold with respect to the Riemannian volume, then this limiting differential operator L would be the Laplace Beltrami operator up to a sign. So some challenges in the use of spectral embedding, because we have already introduced the spectral embeddings or given the eigenvectors of graph Laplacian, it can be viewed, or in the limiting sense, as a function evaluated as at the data points. So one may ask, what if we are given some like data points that was not used in the building of the Laplacian matrix? So suppose today I have like 10,000 points for you to build the Laplacian matrix, and we computed the graph Laplacian and its eigenvectors, and now the other one give you like a new 20,000 data points for you to evaluate the value of eigenfunctions or the embeddings of these new data points. Do you have to evaluate the eigenvectors constructed by these 30,000 data points again? So when the number of data points is huge, one may consider some out-of-sample extension to avoid compute the large matrices again. And also, we have high computational cost if the data size is huge to compute the eigenproblems of this spectral embedding. Classical methods include, for example, nice-join extension that is mostly widely used in the classical spectral embedding. So basically, we given the data points, we compute the graph Laplacian and its eigenvectors, and we use the new data points, just compute the affinity with between the new data points and the old data points to get the nice join extension to get the embedding for the new data points. And more recently, we have some neural network methods to provide some dimension reduced embeddings of data points. For example, SamSNet and diffusion nets, and also variational diffusion autoencoders, and also SpectralNet. We call it SpecNet2. So this work, SpectralNet, also proposes a neural network approach for the spectral embedding or computing the eigenfunction or eigenvectors of a graph Laplacian. So this is most related to our work. So we would refer to it multiple times. We would call it SpecNet1 and our work as SpecNet2. Okay, so our contributions would be, the first, we propose a new spectral network called SpecNet2, which is trained with an orthogonalization-free training objective and allows updating the graph neighbors of the mini-batch. And secondly, we prove the global minimum of the orthogonalization-free objective and reveal the leading eigenvectors of the graph Laplacian matrix and the convergence of the iterative schemes of our proposed different gradient approximation schemes in the linear algebra sense. And last one is we also use some numerical examples to demonstrate efficiency and advantage of SpecNet2 over SpecNet1. For example, our neighbor scheme is better than neighbor scheme of SpecNet1, and also our neighbor scheme is better than First, we review the previous proposed SpecNet1, which also gives us some approximations of the eigenfunctions of graph Laplacian matrices. So first, the optimization objective of SpecNet1 is the constraint optimization. So F1y is the trace of Y transpose times, so I minus D to the minus half times W times D to the minus half. So this one, so I minus this matrix is called the symmetrically normalized graph Laplacian, and is closely related to our previously introduced random walk graph Laplacian, and we will explain it later. So basically, they want to solve this constraint minimization problem because its minimizer gives you the eigenvectors of these graph Laplacian matrices. And the approach to solve this constraint minimization problem is to use the minimatch gradient evaluation. So basically, given any batch of data points, say B, and they solve this surrogate constraint minimization problem. So where they want to solve the array evaluated at current batch B, and where WBB is the principal submatrix of W, whose row index and column index are both at the current batch. And D tilde B refers to the degree matrix. So remind you that degree matrix is just the row sum of this affinity matrix. So D tilde B refers to the degree matrix only computed by the WBB matrices. So suppose this is to say that we only have the current information at current batch, so no information of the affinity entries outside of this current batch. Okay, so we call this reduced problem as a local evaluation scheme, and we will have two more schemes, which is called full and neighbor schemes. So let's just keep that in mind. This is what we would call local. And SpecNet2 construct the neural networks. So basically, this neural network for the computation of spectral embeddings contains two parts. The first part is generally a general network mapping, so maps any point from Rm to Rk. And then this network is appended with a linear orthogonalization layer. So this matrix is computed by the Cholesky factorization of the embedding of the current batch. So basically, we want to orthogonalize the output of the current batch at each batch step, such that the output of the current batch would be first the network embedding and times, so multiply with this k by k matrices to correct its to rotate it as the such that its columns would be orthogonal to each other. And then they update the weights theta. So theta is the network parameterization for the first part, and using the gradient of f tilde 1 evaluated at this point. So this point is referred to as the network embedding of the current batch. And they use the gradient of this to update theta, and then keep the orthogonalization layer unchanged. Okay. So one question is, because we have involved the orthogonalization in this framework, so exact orthogonalization needs access to the whole data set, right? So would this raise any trouble? So we will see. And based on the SpecNet2 framework, we consider if we can replace this constrained minimization problem with an unconstrained optimization. So let's recap that our goal is to compute to the leading eigenvectors of the random walk graph Laplacian, which is I minus D inverse W, and which can be viewed as a generalized eigenvalue problem with the matrix couple, which is WU equals DU and times a capital lambda, and with some normalization that satisfies U transpose DU equals n squared times I. So this is not a constraint, it's just a normalization to make sure that each entry of U is of order 1. And so compared to the constrained optimization problem as shown in SpecNet2, we propose to solve an unconstrained optimization problem, so whose solution also gives you the eigenvectors of these Laplacian matrices. Okay, so many previous work use this unconstrained minimization problem for solving the standard eigenvalue problem. So where the D is equal to the identity matrix, so it's the standard eigenvalue problem. If we replace So previously, if we replace D with I, then it's a standard eigenvalue problem. And now we are focusing on the generalized eigenvalue problem. So for the standard eigenvalue problem, the optimization problem typically solve this square of the Frobenius norm of this W minus array Y times Y transpose. So this is a non-convex and also without any constraint optimization problem. So it was shown that the minimizer of this can reveal the leading eigenvectors of the matrix W. So we basically extend the unconstrained minimization problem for the standard eigenvalue problem to the generalized eigenvalue problem. Okay, so our formalization for the optimization objective for our generalized eigenvalue problem is as follows. So we propose f2y equals, so 1 over n squared is just some scaling factor, equals some trace of minus 2 times y transpose wy plus also some factor y transpose dy times y transpose dy. So we just generalize the square of the Frobenius norm to accommodate with a generalized eigenvalue problem. And also we can compute the gradient of this F2y, so which gives us minus 4 w times y over n and plus 4d divided by n cubed times y transpose dy. So this is the gradient of F2 up to a factor n. So it doesn't matter because the goal, for the reason we write here, we divide by n and n cubed, and on the top we divide by n squared and n to the fourth, is that we want to make both of these expressions to be of order 1 when the number of samples goes to infinity. So once we obtain the solution, say y hat, to this minimization problem, we can retrieve the eigenvectors of the inverse W by just solving a Rayleigh quotient. So basically, the final solution U hat can be computed as U hat equals Y hat times some rotation matrix O, where O is a K by K matrix that satisfies Y hat transpose W Y hat times O equals Y hat transpose dy hat times O and times some eigenvalue matrices lambda hat. So U hat is our last product, which gives us the eigenvectors of the Laplacian matrix. Okay. Since typically the first eigenvector of this graph Laplacian matrix is trivial, so it's a constant vector, so it's not of interest to us. So we can modify the expression to skip solving this first trivial eigenvector. So in a way that we replace W by W minus eta times eta transpose, where eta is a column vector. Eta equals D divided by the 2 norm of D, where the vector D is the diagonal entries of the degree matrix, such that once we replace W by W minus eta transpose, the minimizer of this can keep the first constant trivial eigenvector, such that in the final solution, we will not see the constant eigenvector. Also, the gradient of this F2 will be modified or changed correspondingly. So basically, we just change the W to W minus eta transpose. And the second term in the gradient is the same. Okay. And now it's time to introduce the different gradient evaluation schemes for this optimization objective F2. So basically, we will propose 3 different evaluation schemes. First is full evaluation scheme. So here are 3 figures to illustrate how we make use of the entries of the matrix in W. So first, full invariant scheme means we use at the current batch, we use all the affinity information of the whole data set in the column directions. And the local scheme refers to at the current batch, we only use the current batch affinity information in the column directions. And the neighbor evaluation scheme refers to at current batch, we use all the neighbor affinity information of the current batch in the column directions. Okay. So in more detail, so first, the local evaluation scheme, we use this to approximate the gradient of F2. So first, W will be replaced by WBB. So where WBB refers to the principal submatrix of W that whose row index and column index are both at the current batch. And also eta B tilde is computed by the current the principal submatrix WBB. So as D tilde divided by the two known of D tilde, where D tilde is the diagonal entries of D tilde B. So D tilde B is the degree matrix computed only using the WBB. So it's a reduced problem. And also for the other terms, so we will replace D by DB tilde and all the Y by YB, such that the iterative algorithm would conduct an update of this as YB. So YB is so our goal is to solve the optimization problem. So where the array is Y, so YB is the index of the array corresponds to the current batch B. So we update the current batch as YB minus some step size times this local gradient. So this is the local scheme. So you can imagine that when the data points are relatively well separated and W is very sparse, which means most entries of W is 0. So WBB for most batch would be nearly diagonal. So this local scheme may not be a good approximation unless you choose a very large batch for like a sparse graph. And also we can view the straightforward evaluation called the full evaluation scheme. So the full evaluation scheme as approximation to the gradient of F2 can be written as WBX. So B is the row index and X is the column index. And minus eta B. So eta B is the batch index of the, so is the sub array of this eta evaluated at the current batch. And eta transpose, here we use the 4 entries of eta and times the Y. So where we make use all the informations of the array Y and plus 4 times the degree matrix at the batch side at the current batch and times the array Y at the current batch and times this Y transpose dy, where we again use all the information of the array. So basically, this is just a batch version of the full gradient of F2. So we just take out its row whose index refers to the current batch. Okay, so the iterative algorithm scheme conducts update as, so we update at each batch step, we update the current array evaluated, current array at the current batch index as, again, YB minus some step size times this full gradient approximation. So actually, this is not approximation. This is exact gradient of F2. So take out the batch rows. And this update is basically the block coordinate descent. And the main cost of the computation would lie in eta t, eta transpose times Y, and also the Y transpose dy, where we use all the informations of the whole array Y to do the matrix multiplications. And for the neighbor scheme, where we want to reduce the computational cost of the batch of the whole array, where we use the whole information of Y. So before that, we define the neighborhood of the current batch as neighbor of current batch equal to all the set where Wij, the affinity between the points and the current and the points in the current batch is non-zero for any xi current. So xi is the batch point. Basically, is the union of all the neighbor points of each points in the current batch. And neighbor evaluation scheme is written as follows. So first term is still minus 4 over n times this affinity, where W is used as the row index with batch index and column index with neighbor index, and times Y of the neighbor index. So this is the same. Actually, this is the same as WB times WB x times the whole in times Y with the whole index without n. And the second term is the same. Also for the third term, which includes Y transpose dy. And then the iterative algorithm would conduct update as YB equals YB minus step size times this approximate gradient. So you may notice that this neighbor gradient approximation is actually the same as the full gradient evaluation. But the reason we write it here is to for the later use in the neural network sense, where they will be different. And the performance would also vary in the neural network setup. And also for the updating of this eta transpose Y and Y transpose dy, we can notice that eta transpose Y can be written as eta of the sub matrix of eta at the batch index transpose times Y at the batch index plus the complement of the batch index of eta transpose times Y at a complement of batch size, current batch. And also Y transpose dy, we can decompose it into Y current batch transpose D current batch times Y current batch. And also the other term would be evaluated using all the points at in the complement of the current batch. So this formula will be used in the later network approach and show the difference. And at each iteration, we only update eta transpose Y and Y transpose dy only on the batch. So basically, we keep a record of this, and then we at each batch step we minus this the old eta b transpose YB and plus the new one. So in the linear algebra sense, so I can mention it again. So the neighbor scheme is totally the same as the full evaluation scheme, and we will see the difference between in the neural network setup. And before we go to the neural network, I shall mention that we also provide some theoretical results for the convergence of the full and the neighbor updating schemes. So the results were provided back to the original proposition. So where Y is here, we only have W, and the result is totally the same when we replace W by W minus eta transpose. So our results include 3 parts. So the first, the local minimizers of this unconstrained optimization problem are of the form. So given by Y star equals U sigma times Q, where Q is a K by K matrix. He knows Q can be any orthogonal matrix. And also, any local minimizers of this unconstrained optimization problem is a global minimizer, such that we can solve this by using the gradient. And also, we provide the convergence result. So basically, when the step size is sufficiently small.
Sorry to interrupt, but you only have 5 minutes left.
Oh, really? Okay. The iteration with 4 neighbor scheme converge to a global minimizer for all the initiation with a boundary region. So this is pretty standard for the in the numerical linear algebra sense. Okay. So we can also have some gradient evaluation schemes for F1. So basically, since this is already proposed in previous work, so we can skip this. So basically, and I shall mention that the orthogonalization of this can be solved in using the Cholesky decomposition of y transpose dy, and we can also do the neighbor update for this y transpose dy decomposition, such that and the convergence of this is also straightforward because it's a traditional projected gradient descent method. And okay, this is the linear algebra results of these different gradient evaluation schemes. So basically, we compute the spectral embeddings of the one move. So where we have 2,000 samples, which batch size 4, and the average number of batch size 4 is about 620, such that we can see that net1 4 and net1 neighbor, and also net2 4 and net2 neighbor can give very good convergence result, but not with local for either net1 or net2 in the linear algebra sense. And also, we can have neural network optimization for SpecNet2. So basically, we compute a network mapping from Rm to Rk that approximates eigenfunctions of L. And also, the network output of the current data set would be the approximation of eigenvectors of the graph Laplacian matrix. And the learning objective is the F2 we proposed. And because the gradient formula, we can incorporate our previous 3 different gradient evaluation schemes to this. So one difference in the neural network setup is that the linear algebra, in the linear algebra sense, we can just update y on the current batch B, but in the neural network sense, we are actually updating theta. So y on B, a complement of B theta would also change if we change the network parameterization. Okay, so how we work in the neural network sense? So basically, we first compute the neural network mapping of the current batch and plug it in to the local evaluation scheme. And then we minimize the trace of the current batch, output of current batch transpose times this gradient by plugging in, where we parameterize this y of current batch is parameterized by theta, but the gradient term is detached, and use this to update parameterization theta. And also, for the full scheme, we do the same thing. So it's plug in and minimize this, detach the gradient, and use the gradient with respect to theta of the first output to update theta. Okay, so the main part is in the neighbor scheme. So where we, in the update, we keep a record of 2 matrices, which is y transpose dy and y0. So as we talked about earlier, at each batch step, we update y transpose dy only on the current neighbor of the current batch, such that we will minus the old y dy on the neighbor and plus the y dy evaluated on the neighbor for the new one, and also update the y0 accordingly. And then we use these 2 records to compute the neighbor scheme. Okay. Again, use these 2 formula to update theta. And also, we can accommodate these two different schemes in the training of Net1. And we should point out that the performance of SpecNet1 improves dramatically if the orthogonalization layer is parameterized also by theta.
You actually only have 1 minute, so
yeah.
you should.
So let's see the numerical results for the final. Okay, so first for the 1 moon result, we have 2,000 samples for training and 2,000 samples for testing. And you can see the approximation of the eigenfunctions using these 2 different networks with 3 different schemes is can be seen in these 4 subfigures, where we have seen the SpecNet2 full and neighbor can provide very good results, but not with local. And SpecNet1 neighbor cannot provide good result, especially in the second approximation of the second non-trivial eigenfunction. And also, if we compare Net1 neighbor with Net2 neighbor on the unsupervised classification of these 2 moon results over 10 different random initializations, we can see the result given by Net2 neighbor is more reliable and has less variance. And the last result I want to show is the MNIST result, where we have 20,000 images for training and 10,000 images for testing, and we build 0,1 KN graph where we choose K to be 16. So the main purpose for this experiment is to compare SpecNet1 local with our Net2 neighbor when we view the main computational cost is the network evaluation. So we compare Net2 neighbor with batch size 248 with Net1 local with batch size 45, 90, and 108. So you would see if we use the loss of F1 and F2 as the criterion, we will see in particular Net2 neighbor with batch size 2 and show in the bottom line here, and compare with its corresponding batch size in SpecNet1 local, which is 45, which is top one here. So you can see the difference is significant when we compare these two. Okay, so in this sense, we would say Net2 neighbor would also outperform Net1 local with comparable batch size in a very sparse graph. Okay, here is the embedding. And for the future work, so basically we want to provide some theoretical result in the neural network setup beyond the linear algebra sense, and also construct an affinity graph in a different way. And the last one would be the explore more real-world data sets using our SpecNet2. Okay.